Hello and welcome to Plant Breeding and Genomics Community of Practice webinar. The title of today's webinar is The Introduction to the rrBLUP package for R for Genomewide Selection. My name is Sean Yarnes. I'm the Content Coordinator for PBG and your host today. For those of you who are unfamiliar with Plant Breeding and Genomics Community of Practice, or PBG, I invite you to explore our training resources at www.extension.org/plant_breeding_genomics. I also invite you to subscribe to the PBG newsletter and follow us on Facebook and Twitter to stay up to date with PBG webinars and news. During today's webinar, Amy Jacobson will provide an introduction to the rrBLUP package in R and perform sample analyses using data from the Tritiaceae Coordinated Agriculture product. Today's presentation, as well as Amy's data set and the R program, are available at http://pbgworks.org/node/1440. The webinar recording will also be posted here within the week. After the 45-minute presentation, you will have the opportunity to ask questions. If you have a question, you can simply type it into the question box on your screen and hit return. If you can't see the question box, click the small plus sign next to the word question on your control panel to open it up. We'll answer as many questions as we have time for in the 15-minute panel period. After today's webinar, you will receive an email asking you to fill out a brief survey evaluation. Please complete this evaluation so that we may better tailor our webinars to your needs. Please welcome today's presenter, Amy Jacobson. Amy is a PhD student at the University of Minnesota, advised by Dr. Rex Bernardo. Amy received her bachelor's degree in plant science from Cornell University in 2011. She is currently researching improving accuracy of genomic selection in maize biparental population. I will turn things over to you now, Amy.
All right, thank you, Sean. So, like Sean said, I am a PhD student at University of Minnesota, and I will be talking today about the introduction to genomic selection in R using the rrBLUP package. And we're going to start out here first with a poll of just to get an idea of what your experience is in using R. So if you could select one of the choices, whether it's your first time using R, if you use the basic base commands in R, written code in R, or are proficient in coding in R. Just a little background about my experience in R. I took 2 undergraduate courses in R and learned basically the base commands and how to do some writing code in R. And then from there, I've just been looking online at sample code and trying to use that sample code for my own work here. So looking at the results here, it seems that most people have either this is their first time using R or they've used basic commands in R. So just going through the webinar, I'll be sure to explain more about the basic commands and how to use those commands in rrBLUP. So going back to our learning objectives for today, first I'll go through how to download the package and load the sample files. Like Sean said, the sample files are from the TCAP project and are available online. I'll then go through imputing missing markers using the a.mat command, define the training and validation populations, and then finally run mix.solve to determine the accuracy of the predictions. So just a little overview of the ridge regression BLUP package. For the package to work, you must be using R version 2.14.1 or greater, and I recommend using the latest version of the package, which is version 4, which came out in September. For the code that I'm presenting today, you will be needing to use the version 4 package for the imputation, and must be using the R version 2.14.1 or greater. This package uses ridge regression BLUP for genomic predictions and uses the mix.solve command to predict the marker effects. Mix.solve does not allow for any NA or missing markers, so imputation is necessary in order to run the command. And the package also allows you to define the training and validation populations for genome-wide selection. So just a quick overview of genomic selection. There's either a one-step or a two-step process. I'll be using the two-step process. The two-step process uses the adjusted means calculated across locations, and then these means are then used for ridge regression BLUP, while the one-step process uses the mixed model analysis for the plot data. So I'm using the two-step approach since the data set only has one location, so there really aren't means that need to be adjusted across locations, and this is also computationally more efficient and faster. So to install the package, especially for the people for the first time that they're using R, you have to launch R, go to the Packages menu, and then Install Package, and then select the CRAN mirror nearest you. A lot of locations will show up, so just select where you are. Then a list of packages that are available on CRAN will show up, and select rrBLUP, and then hit OK. Another way to install packages is to install them by a zip file. So if you go to the CRAN website for ridge regression BLUP, and then load the package by going to the Packages menu and then Install Packages from local zip file. And then just select wherever you've saved that zip file that you downloaded online and just hit Open, and that will load the package too. So now that the package is installed, the library must be loaded every time R is open. So to do that, it's just the library and then parentheses, whatever package you're using. So in this case, it's rrBLUP. And this is done every time that R is open, the library must be loaded. So just an overview of the sample files that I'm using. The files were downloaded from the Hortium Toolbox from the TCAP project. And this is a University of Minnesota barley breeding program preliminary yield trial from the St. Paul location in 2009. I selected 3 phenotypic traits to use. I selected yield, plant height, and heading date. I selected these traits since they have a pretty high heritability for plant height and heading date, and they were easy to be measured, and so all the individuals had these numbers, and there were no missing values. The marker set had 1,178 markers, and 164 of those markers are NA, and we'll go through with imputation what to do with these NA markers. The data set was also in the format that's needed for the rrBLUP package, and this is that the markers must be in a -1, 0, or 1 format. So the 1 is the SNP for the homozygous parent 1, 0 is heterozygous, and -1 is homozygous SNP for parent 2. So the sample files are available online, and once you download those files, you can set the working directory in R using setwd and put in the local directory that these files are saved at. So you can see from the screenshot that my local directory was my computer, then documents, and then I had a webinar folder where these sample files were saved. And to load in the files, I used the read.table command. Since this was a text file, if I was using a CSV file, then I would use read.csv. And the header, there is a header in the marker file. There is not a header in the marker file, so I have header equal to false. And I then used the head command in order to see that the files were loaded correctly. So I did head markers, and this shows the first 5 lines of the file, and it also shows the column names. So I can see that a header was not put in since I had header equal to false, and I see that the data was loaded incorrectly, that there isn't a header, and that the sample file looks like it does in the text file. So this is always good to see, to make sure that the files have been loaded incorrectly, and that will help out later on, make sure that we don't have any error messages. So to load in the phenotype files, the phenotype file does have a header. So I have header equal to true. And for the phenotype files, there are 3 phenotypes of yield, plant height, and heading date. And using the head command, I can see that that file has also loaded incorrectly and that there is a header with yield, height, and heading date. And all of these files must be in matrix format. So when I load it in, and in the code, it's as.matrix, and this converts the files from a table to a matrix, which is necessary for the package. So to also make sure that the sample files have been loaded in correctly, we can determine the size of the matrices. So I did that with the dim command. And to do dim markers, this shows 96 individuals, which is what was 96 observations that we had for the phenotypes and the markers, and then 1,178 markers. So this is 96 rows and 1,178 columns of the markers. And then for the phenotypes, it's again 96 individuals and 3 traits. So 3 columns for the traits. Okay, so then moving on to our next learning objective of imputing missing markers using the a.mat command. So rrBLUP mixed solve does not allow for missing markers, so NA values are not allowed, and if NA values are in the matrix, an error message will come up. So the imputed value for my code is the population mean for that marker. And this is useful for SNP data since the level of missing data is pretty low. In the sample file, we had 164 markers that were NA out of 1,178 individuals that all had out of 96 individuals. So this is only 0.14% missing. So it's a very low amount of missing markers. So imputation can be done without any adverse effects. And this command also calculates the additive relationship matrix, but we won't be using that today in the code. So for the impute code, the first is the markers, and this is the matrix that needs to be imputed. And the max.missing I have set to 0.5. So this is the maximum proportion of missing data that is allowed. So if more than 50% of the markers are missing data, then the markers are not imputed, and these markers should then be removed. This is a good quality control since you're removing markers that most likely were just not genotyped correctly and really aren't helpful to the analysis. And the impute method is the mean, since we're imputing the population mean for that marker. And I have return.imputed equal to true, so since I want to see the printout of the imputed results. So just in the code to rename some of the matrices, I renamed the marker matrix to the imputed marker matrix, just for later on for the mix.solve. And the outputs from the imputed command, the imputed returns the imputed marker matrix, while the $A returns the additive relationship matrix. And here's a screenshot of the printout of the imputed marker matrix. So you can see in this red box at the top, this is the imputed marker value. This marker used to be an A, but after imputation, the population mean was 0.8. And with the marker V169, the marker values were left NA since more than 50% of the data was missing for this marker. So this entire column needs to be removed since this marker is not helpful to our analysis. So in order to remove markers that had more than 50% missing data, there were 2 columns that need to be removed that had NA after the imputation, and this was column 169 and column 562. And just to remove them, it's just the minus C and then the column names that need to be removed. And the new dimensions you can see show 2 less columns. So these are the 2 markers that have been removed. And I then renamed this matrix again, markers impute 2. And this is the marker matrix that we will be using for our analysis. Okay, so going on to our next learning objective, to define the training and validation populations. So for genome-wide selection, we need to designate what the training population is and what the validation population is. So the training population is genotyped and phenotyped, while the validation population is what we're trying to predict. And this is the phenotype values estimated based on the marker effects calculated from the training population. So the validation population is only genotyped, but then we're estimating those phenotypes. And in the code, I have it set so that 60% of the total population is the training population, while 40% is the validation population. And then we'll do correlations in the validation population of what was actually observed and what we predicted. So for 60% of the total population, that's 58 individuals. So 58 individual numbers need to be sampled in order to determine which individuals are in the training population. And to do random sampling in R, it's just the sample command. And I create a vector of these random numbers. So it's sample 1 to 196, since those are the numbers that we need to sample in between. And then we sample 58 of those numbers in order to get the training population. And so these end up being the row numbers of our marker matrix and our phenotype matrix. And the sample numbers are different every time the code is run, since these sample numbers are different every time. And this will affect the correlation accuracy. So you need to run for many iterations in order to get a better estimate of the correlation accuracy. So if you're running the code and you see different output here, that's just because R is sampling different numbers than what was sampled when I ran it. So these are the column. This is just the head command. So the first 5 random numbers that were sampled. And so these are the row numbers that we will use in the training population. So in order to get the row numbers for the validation population, I use the setdiff command. And this just gives us the numbers that were not sampled in the training population. So it's the validation population. And these are the 38 individuals that we will keep in our validation population. And again, if you're seeing different numbers and you're running it, it's just because R sampled different numbers than what was sampled when I ran it. Okay, so to set the training and validation matrices, I renamed the pheno_train and marker_train as the phenotype and marker matrices for the values in the training population, while the pheno valid and the marker valid are the matrices for the validation population. So this just goes through and selects the row numbers that were sampled before in the slides before for the training population and the test population. Okay, so now to run mix.solve and to determine the accuracy of these predictions. So this is the equation for genomic selection. And to go through the equation, the y value is the n/1 vector of the phenotypic means. And this is the pheno_train matrix that we created in the slide before. The mu value is the overall mean of the training set. And this is output by the mix.solve as the $beta. And then X is the n by number of marker matrix. And this is the m_train marker matrix that we created in the slide before. The G value is the marker effects matrix, and this is what we're solving for in ridge regression BLUP. This is calculated in mix.solve as the $U. And then E is a vector of residual effects. So to input into rrBLUP, we input the pheno train, the marker, and the marker train. So to run the code for rrBLUP, the first trait is yield. So I set yield equal to the first column of the phenotype matrix. Then I did mix.solve for a vector, excuse me, for a vector of the observations. And then I set Z equal to the marker matrix. And K is equal to the identity matrix. So K equals null. And then I have the standard errors and the return hide as false. So after running this command, I have the yield answer and $U as the marker effects. And E is then reset that to equal to E. So E is the matrix of the marker effects. And this just shows the head command for the E marker matrix. And so these are the marker effects for individuals from the validation population. So once we have the marker effects, we need to multiply it back to the markers in the validation population. So to do that, you multiply the M valid, which is the marker validation matrix, times the marker effects. And to get the actual value, the predicted values for the yield, we need to add in the overall mean, which was seen in the equation a few slides back. So to get the predicted yield, it's the predicted yield based on the marker effects of the training population with the grand mean added in. And the grand mean is the $beta, which is output from the mix.solve command. So this is the predicted yield of the 58 individuals in our validation population. And then we can compare those to the observed yields that we saw actually in the field. So in order to determine the correlation accuracy, we use the core command, and I set the yield the yield validation as the first column of the phenotype matrix that we put in before, and correlated that to the predicted yield values. And so the yield correlation accuracy was 0.25. And again, this number will change based on what individuals you have sampled. So the 0.25 will vary a little bit based on the individuals that were sampled in the training population. So once we have the code set up, it is simple to run for many different traits. So for plant height, that's the second column in the phenotype matrix. And to correlate that, it's the same code that we ran for yield. Well, this is just an output of the code, and then the accuracy based on plant height. So you can see that the accuracy for plant height is 0.4, which is greater than the 0.25 that we saw for yield, which is expected since plant height has a much higher heritability, and so you expect the correlation accuracy to be higher. And then for the third trait, for heading date, this was the third column in the phenotype matrix. And again, correlating, running mix.solve to get the marker effects, and then multiplying the marker effects to the validation marker matrix. And then running the correlations for the predicted values and the observed values. And heading date was even higher than plant height and yield, and for accuracy of 0.52. And if you're running this as you're watching, you probably have a different number, but it's probably pretty similar, just based on what individuals you put in your training set and validation set. So in order to get a better accuracy, get a better guess of correlation accuracy, it needs to be run for many iterations. So I did a for loop in R to run 500 iterations of mix.solve and then took the means of those correlation accuracies from the 500 iterations. And the accuracy for yield with just one iteration from before was about 0.2, but running it after 500 iterations, the better estimate was 0.23. So it's not a big change, but it's definitely a better estimate. And to do that, I set the traits equal to 1 since we're just estimating one trait now. It's just yield. And cycles equal to 500, so that's 500 iterations. And then I created an accuracy matrix of the number of cycles and the number of traits. So it's a matrix of 500. And then I ran mix.solve 500 times and got 500 correlation accuracies in this accuracy matrix, and then just took the mean of the matrix. So it's a simple loop that's set up in order to run many iterations of mix.solve and get a better correlation accuracy. So again, the correlation accuracy is different for each trait, and the values will be different every time it is run, since different lines will be included in the training or validation sets. And accuracy is affected by many things, including training size, validation size, number of markers, inheritability, and even just the trait itself. So I just wanted to show here that the number of individuals put into the training set has a big influence on accuracy. So if you see here, with 10% of the individuals in the training population, the correlation accuracy is pretty low. But when 90% of the individuals are put into the training population, there's a lot more information to estimate the marker effects, so the correlation accuracy goes up. And this is seen in many of the literature on genomic selection. So just to go through some common errors, I know when I was creating the code, I probably saw all of these errors, and errors are pretty common in R. And to get around that, I usually just Google the error message and see what comes up. Usually other people have had this problem too, and they can help of ways to solve it. So for this error, the headers were incorrectly input. So if I put the header equal to false for the phenotypes, the headers then go into the first line of the phenotype matrix. And once I run mix.solve, it says that it requires a numeric matrix. So these headers were put in as non-numeric and as characters. So the marker matrix cannot multiply in mix.solve. And if there are NA markers, if the imputation, if you didn't impute or set the NA markers equal to 0, there will be an error message that comes up saying that there's infinite or missing values in X, and X is your marker matrix. So you can go back and see where these missing markers are and whether to impute or just remove the marker. Another common error is to have an incorrect matrix dimension. So for this error, I removed one individual from the phenotype matrix. So it had 95 individuals in the phenotype matrix, but had 96 individuals in the marker matrix. And a couple error messages come up that way. And usually the subscript out of bounds will come up, and this says that you have more individuals in your marker than phenotype matrix, and the matrices cannot multiply then. And then as you keep on running the code, the correlations or mix.solve will not run. So another common error is to read in the values as characters instead of numeric. In R, this happened because the header was equal to false. So grain yield and plant height and heading date was read in as characters since they're letters instead of numbers. And this is easy to see because there's quotes around the values. If there's quotes around the values, then it's a character matrix instead of numeric. But you need a numeric matrix in order to run mix.solve. And so to do that, to fix this, you would just set the header equal to true. And then the first line would be a number, and it would read in as a numeric matrix. So there are a lot of resources for R available. The rrBLUP reference manual and the vignettes online are very helpful. These show examples of how to run rrBLUP and explain all of the variables that go into the equations and that go into the code. So I definitely recommend looking at these first and running the sample data sets available there, and then trying to change that code to make it run for your data set. The rrBLUP was published in this paper in Plant Genome from Jeff Endelman, who created the package, and the paper is very helpful to look through to see how the package runs and what equations it is using. So just a couple of the acknowledgments. I'd like to acknowledge my advisor, Rex Bernardo, and also all of the students in my lab. Emily and Leanne have helped me a lot with coding, and especially for this webinar, and also Chris and Lisa Marie. And Jeff Endelman for writing the rrBLUP package. And my funding is from Monsanto and the USDA SolCap for the webinar. And also the SolCap, people have helped with the webinar, and the data set, which is from the TCAP Hortium Toolbox. So I guess we can go here to questions.
Okay, thank you, Amy.
Now we'll have now we have about 15 minutes to answer questions. For those of you who missed the beginning of the presentation, you can use the question box on your screen to type in questions and hit return. If the question box is closed, you can click the small plus sign next to the word to open it up. I'll be reading the questions out loud, and we'll answer as many as we have time for. Let's take a look at the questions. So the first question asks, what about selecting for traits with low heritability? Isn't this one of the benefits of BLUP?
Yeah, you can definitely select for traits with low heritability. Correlations probably won't be as high, but it is an advantage. And since phenotypic selection with low heritability, the correlations are low there too, there will be an improvement with genomic selection. So it still can be done, it's just the correlations won't be as high.
Okay, and the next question we have is, can this rrBLUP be used in association mapping?
I don't do anything with association mapping, so I don't think ridge regression BLUP is used in association mapping. I think you're better off using software like Tassel for association mapping, but using rrBLUP is mainly used just for genomic selection.
Okay.
Since we're not really, accounting for population structure here as you would in association mapping.
And we also have a question asking you to clarify what you mean by a training population.
Okay, let me go up. Slide. Okay, what I mean by a training or validation population, what was the question again?
It was about the training population.
Training. Okay, so the training population is basically what you're training your model off of. So it's the population, it's the subset of your population that was genotyped and phenotyped. So these are the markers and phenotypes that you're putting into your model. And then the validation population is the predictions based on the model you made with your training population. So it's how you get your phenotypes based on the marker effects calculated from the training population.
Okay, and the next question is, how will you adjust the mean phenotype in the two-step rrBLUP? Will that give you the same result as the one-step?
So you will not get the same result. I've only done work with two-step. I haven't done anything with one-step yet. So you will get different results. But for my for this data set, there was only one environment. So there were no means. There was only one environment that I could use in this data set. But otherwise, if you're doing adjusted means, it's a two-step since you're adjusting for the means and then putting those adjusted means into the rrBLUP. But if you're doing one step, it estimates it all at once. So it is different numbers, but I haven't done any work with that personally, so I don't know how different it would be.
Okay, and the next question is, why not use the kinBLUP function instead of mixsolve?
I haven't used kinBLUP since I don't really have any information on kinship of individuals, and for this data set there wasn't any information on that either. But it can be used if you have that type of information, but it wasn't available in the sample data set. And for my research, I've just been using mixsolve.
And we have several questions asking if this will be online, the webinar, and in a few days it will be online, and it'll be online at pgbworks.org/node114. So that's the answer to that question. Let's go on to another one for Amy. How do you select markers if your assumption of even distribution of genetic causation? Is your assumption of even distribution of genetic causation?
Yes, yeah, that is the main assumption of genomic selection, that all markers have effect and all markers have the same effect. So to select, you don't select markers. Basically, you're using all the marker information that you have to put in your model. Since the more markers you put in your model, the better estimates you're going to have. So the only markers I ever take out are the markers that do not have enough information or have more than 50% missing. But otherwise, you're not selecting markers based on QTLs or anything like that.
Okay, and another question is, do you know if a multi-trait index can be accommodated in the rrBLUP package?
I don't know whether it can or not. I'm I'm not sure if multiple traits can be. I don't think that they can at this point. For now, it's best just to do one trait at a time and then do a selection index based on that. But I don't think you can put a selection index right now.
And another question is could you describe how genomic selection is used in current breeding programs?
Current breeding programs. Well, I know at University of Minnesota for barley, they have incorporated genomic selection into their public barley breeding program. But in industry, I really don't know what's occurring there.
And another question is, can we use other methods to impute the mean, like for imputing marker dosage in the case of polyploids?
Imputing based on polyploid. Yeah, I'm lucky enough to work with diploid species. I work on corn, so I really haven't come across that issue. I'm not sure how you would impute based on the mean if you did have a polyploid. And I know that the code for the a.mat command probably can't handle polyploids to do that, so I'm not entirely sure how you would do that.
Okay. And another question is, what is a good population size?
Good population size. That depends on the trait that you're looking at too. It's hard to just throw out a number, but obviously the larger your population size, the better estimate you're going to have. So it really depends on what trait you're using and how many markers you have. But I would say as big as the population size can be, or as big as your experiment really is.
And another question is, why did you not include a K matrix in your model?
I really just didn't have that information. It wasn't available on the TCAP website, so I wasn't able to incorporate that.
I think this question, next question might relate to the kinship question earlier, but is
Mm-hmm.
there a way to sample for the training set that accounts for pedigree information?
Yes, yes. If you have that information, there definitely would be a way. But again, I didn't have that information, so I couldn't really add that in to this webinar.
Um, and how large a training population is usually recommended?
That kind of goes back to the other question that was asked before of how large should your population be. It in the articles, it's different. I've seen the 60/40 that I used in this webinar. I've seen that in papers before, but it it really depends on the species that you're working with and the trait that you're working with. Again, you're going to have larger correlation accuracies if you have a larger training set, but sometimes that isn't possible. So it really just depends on what experiment you're running, but I would say the larger the training set, the better accuracies you're going to get.
Okay, and this question I don't understand, but maybe you can address it. Maybe it's just a comment. It says GAPIT can run both AM and GS. Do you have any response to that?
And sorry, could you say it again?
It says GAPIT, GAPIT, can run both AM and GS. I don't know.
Okay. No, I don't.
Okay. Here's another question. Can it still be used if phenotype values are not normally distributed or variances are heterogeneous?
I'm sorry, could you say that one more time?
Can this still be used if phenotype values are not normally distributed or if variances are heterogeneous?
If phenotype values are not normal. Yeah, it definitely can still be used if phenotype values are not normally distributed. Um, I'm sorry, what was the
And it says,
variances?
I think better variances are heterogeneous or large variances maybe
Large.
in phenotypes.
Yeah, I mean, the more diversity you have in your phenotypes, the better your accuracies are going to be. So I would say it doesn't have to be normally distributed. Um, I'm not sure about heterogeneous.
Okay. Does the ridge regression method account for non-additive effects or strictly for additive genetic variation among lines?
Um, yeah, I'm not sure about that. I would have
Okay.
to look at that more.
Um, and then I've got a question that's really more for me is, can I repeat where a copy of the presentation and the sample data can be acquired? And you can go to the pgbworks.org website, and it's /node/144, or if you just go to the website, there's a link right from the main page. All right, another question for you, Amy, is please clarify the difference between one-step and two-step methods and why you would choose one over the other. What about G times E in this choice?
Okay, let me go back up to the slide. Okay, so I use a two-step approach basically because it's easier and faster. The two-step, basically what you're doing is you're adjusting your means across locations and accounting for G by E, and then putting those adjusted means into your ridge regression BLUP. While in one step, you're doing that all at once. So it's harder computationally, and it takes longer. But since for this data set, since I only had one environment, I really didn't have to worry about one step, two step, but I just wanted to clarify that there are two methods, whether you're going to adjust your means at the beginning or not.
Okay, here's another question. If I have a set of corn lines and all crosses between them, the lines have phenotypes and genotypes, but the hybrids have only phenotypes. What would be a good strategy to train the model?
I'm sorry, could you just repeat that again?
I can. If I have a set of corn lines and all crosses between them, the lines have phenotypes and genotypes, but the hybrids only have phenotypes. What would be a good strategy to train the model?
I would just use the inbred genotypes and then base your predictions off those inbred genotypes and then select your hybrids based on that.
Okay.
Just as long as you're using the same tester.
And here is the next question. How do you tune lambda? Are there any guidelines for setting the bounds?
Not that I know of. I don't think there's any guidelines on setting the bounds based on lambda.
Okay, and I think this question is similar to one we had before. How does the efficiency differ from diploid to polyploid if we use the same percent of training populations?
I don't really think that there's anything out there that I've read based on that, but it probably is less efficient in a polyploid base as a diploid.
And then we have another question is, how do you check the accuracy of the model from that you validate?
If you use cross-validation and run many iterations, that's the best way of knowing if your model is correct or not.
And then here's another question. Is the 50% empirical for removed markers?
I mean, you could set it to whatever you would like based on the code. I just used 50% since that was easy for this data since it's only 2 markers really were genotyped incorrectly and needed to be removed. But you could set it higher if you feel the model needs to be more stringent.
The next question is, do you always ignore the A matrix in the training population?
I do for my research. I ignore it since it's not going into the model that I'm using for mixed solve. Since I'm just using it looking at correlation accuracy, so I ignore it.
Then could you clarify what is the K matrix?
I didn't really mention using a K matrix, so I'm not entirely sure. I had K equal to the identity matrix, I know, and if that's what the question is based on.
Okay. Okay, this is a rather long question, so I'll read it, and I might have to read it to you again. So, oh, this is maybe an answer to an earlier question. KinBLUP will take an additive relationship matrix calculated from marker data. You can calculate the relationship matrix using markers rather than pedigrees. Calculate the relationship matrix with a.mat and then pass this to KinBLUP, which gives you the GEBVs for each individual rather than the estimated marker effects. I think that's a question, an answer to an earlier question.
Okay.
Here's a question. How do relationships between individuals in the training population influence the results? Perhaps that means kinship, I'm not sure.
I would say that they have better results if they're more strongly related
Okay.
due to the higher LD.
If you have correlated traits, do you use both traits in genomic selection, or do you use the average of both traits?
Yeah, that depends. I mean, I would personally use both traits, but you could do them separately and see. I would run both and see.
And then we have another respondent to an earlier question. AM and GS in the earlier question likely refer to association mapping and genomic selection. This is in reference to the GAP-IT question, so I don't think you need to respond to that. Some of these are repeats from earlier questions. You said that you used all markers you have in hand. Is there a role of number of markers in accuracy? How about the risk of overfitting?
Yeah, there absolutely is a role in the number of markers and accuracy. The more markers you have, the better accuracy you're going to have until you have too many markers, and then you're overfitting the model. But you'll see a plateau in the accuracies.
Can fold cross-validation be used for check accuracy?
Yes, yes, absolutely, absolutely. I just did many iterations, but you could absolutely use fold cross-validation.
Oh, wow. So that is all that I have right now. And that, judging by the amount of questions for you, Amy, your seminar was very interesting and helpful for people. So I'd like to thank you all for attending. And if you still have any questions, you can email me at seanyarns@gmail.com, and I'll pass those on to Amy. Thank you so much for joining us. Thank you so much, Amy. And don't forget to fill out the survey evaluation when you get it in your email. Have a nice day.